Okay, hello DC candidate, welcome back to our part 2 of moment of inertia. We are still solving what sample DC questions. So without wasting time, let us proceed with the next question. The next question is, show by integration that the moment of inertia of a thin uniform circular disc of mass 2m and radius a about an axis through the center O of the disc and perpendicular to the plane of the disc is ma square. Okay, so we are asked to show by integration. It means that I'm having a circle, a circular disc like this. I'm having a circular disc. We all know that what this is the center of the disc. So here is the radius of the disc. As I told you, if I want to calculate the moment of inertia about the center of this disc by integration, it should be what? It is a continuous body. I should use integral. I will integrate from so I'll integrate x. It will be x squared d what? Dm. So this is the formula to integrate a continuous body. Then I should look for dm. I should look for the expression of dm. As I told you, this is a two-dimension figure. Why am I saying that it's a two-dimension figure? Because if I consider maybe a small portion of our disc like this, if I consider a small portion of the disc, I consider a small portion of the disc like this. For me to integrate now all, you see that what? I will increase the portion of the disc. I will like go bigger like this, like a circle. I will go bigger and bigger and bigger. So I will increase it like this. It is in two dimensions because I'm increasing both what? Both the radius and also what? When I increase the radius and I increase what? The angle of rotation. I should go 360. You see that it's already two dimension. Increasing the radius and turning is already two dimension. Therefore, here our density here should be what? Should be a surfacic or a area. A surfacic density sigma is okay, and therefore sigma, if I consider like this small portion of our disc, sigma here now will be what? The small mass of the disc divided by what? The small area of this small portion of the disc, and that small area should be what? If I consider maybe the radius of that small disc to be x, therefore I'll have m pi x square. As simple as that. Is okay. Now from there I make m the subject. You see that what? M is simply equal to pi x square sigma. Then if I differentiate it to come out with dm, since I'm looking for dm, I differentiate with respect to x, I'll have what? I'll have pi sigma 2x. Therefore, dm is simply equal to what? 2 pi sigma xd. The xd is the expression of dm. With the expression of dm now, I'll come and replace inside my formula. It means that the integral about the center of the disc is simply equal to what? The integral from 0 to a. Because what? I'm starting from the origin there. I should reach the radius or the circumference, and that distance is a. So I should integrate from 0 to a. I should enlarge this thing from 0 to a of 2 pi sigma x. Remember there was this x square here. Then times x square will be x cubed. Then dx. How do you understand it? Dm is 2 pi sigma x dx. With this x square, I will have at x cubed. When I will integrate now, I'll have 2 pi sigma is a constant. When I integrate x square, I have x to the power 4 all over 4 from 0 to a. So I'll have 2 pi sigma a to the 4 all over 4. No need to replace 0, we'll go. But I know that what? Sigma, the surfacic density or the area density here is what? For the whole disc, it will be equal to the mass of the disc. Then they indicated the mass of the disc here to be, okay, the mass of the disc is 2m. So it will be 2m divided by what? It will be 2m divided by the area. The total area of the disc here is what? The total area of the disc is simply what? Pi a square. Why pi a square? Because what? Because the radius of the whole disc is a. So while replacing here, the moment of inertia of the disc about its center will be simply 2 pi. Rather than putting sigma, I will put what? 2m all over pi a square. Then a to the 4 all over 4. Okay. Then from there, you will see that what? 2 I will have 4 pi m a square all over pi a. Here is 4 a square. Here you cancel here 2 times. There's 4 here. Pi here cancel. This 4 cancel. I will stay with what? M a square. That is the proof. As easy as that. You see that there is nothing there. You integrate. You come out with your value. Okay. Next part of the equation. Okay, so the next part of the equation, the disc is free to rotate in a vertical plane about a smooth horizontal axis through a point A on the circumference of the disc. The axis is perpendicular to the plane of the disc. Roman to show that the moment of inertia of the disc about the axis is 3ma square. Try to understand. The disc is free to rotate in a vertical plane. It means that the disc is free to rotate in this plane. Is okay? In a vertical plane about a smooth horizontal axis. About a smooth horizontal axis through a point A on the circumference. It means that I should choose a point on the circumference where the disc is free to rotate. Are you understanding? It means that this is my disc. I will choose this point A, and this is the center. So the disc is free to rotate about an axis passing through A. So you should understand it. Now, about it's free to rotate through a point A on the circumference of the disc. Okay, this axis is perpendicular to the plane of the disc. It means that what? When we say that the axis is perpendicular to the plane of the disc, you can take it like having a paper like this. The axis is entering like this, perpendicular. So the axis is like this. Let's say it is entering the paper, so that the paper now can rotate like this. The paper can rotate like this. So that is the meaning of it. Means at this point A, the axis is like this. It's okay. It's entering inside A, so that now the disc now can rotate vertically. It's okay. So that is what they are asking. That is what they are saying. In fact, then they are asking us to calculate to show that the moment of inertia of the disc about the axis is this. Very simple. I will use parallel axis theorem here. As easy as that. Because I want what? Let's say the axis of rotation is like this. Is okay. So it means that I will first of all calculate the moment of inertia about the axis of rotation A, because the moment of inertia about the center of the disc plus the moment of inertia, plus the mass of the disc. The mass of the disc there is what? The mass of the disc is 2m. Times the distance separating what? Times the distance separating the two parallel axes. When I say two parallel axes, this is how the axes are. The axis passing through O and perpendicular to the plane, this is our plane. And the axis passing through A and perpendicular to the plane. Are you seeing the two parallel axes? So the distance separating them is what? Is simply what? A, which is the radius of the circle. Therefore, I'll put here what? A square. As simple as that. From parallel axis theory, we come out with a moment of inertia. Okay, students. So the moment of inertia of the disc about the center O, it is half mr square. It's inside the formula booklet. It's okay. Now the mass here, let us replace directly. The mass here of the mass of the disc here is 2m. So it will be half in bracket 2m, and r here is the radius, which is what? A square. So the moment of inertia about point A is simply equals to 2. We can say here I will have ma square plus 2ma square. So ma square plus 2ma square is how many? 3ma square. As simple as that, you have your proof. That was 2 marks. Then Roman theory. Let us proceed to Roman theory. Roman theory show that now they are saying that the disc is released from rest when AO is horizontal. It means that what? When AO is horizontal, so I will draw another diagram here. So I will turn this thing until AO now is horizontal. I will turn it until AO now is horizontal like this. Then I will leave from this position. I will leave it now. It will start rotating. When you will start now rotating, you will come here until a certain value here. Now this is the new value of A here, making an angle of theta with the old position of A. So that is what they are saying, and they are asked now to show that at that position 3a d square d theta dt square is equal to 4g sine theta. Okay, that is simple. That is very simple. Here you should apply what? The law of conservation of energy. As simple as that, because A changes position, it loses potential energy to gain what? Kinetic energy. Okay, so by using P energy, potential energy loss equals to kinetic energy gain. From this formula, the potential energy loss there is simply mgh equals to half moment of inertia about A times who? Times omega square. Okay, now the loss in height here, look at, as I told you, if I take the reference here, the distance from here to here is the initial height, and here from here to the next value of to the final position of A is the final height. So if I calculate that loss, it will be this minus d, which is this distance. That loss in height is this distance h. And you can also see that what? If this is theta, this is also theta. Opposite. The distance from 0 to a is a radius. Therefore, that h should be what? It should be a sine theta, opposite side sine. Okay, then I will come and use here. Please, the mass of this is how many? Is 2m. So I will replace 2m g a sine theta simply equals to half. The moment of inertia we calculated, it was 3m a square, then theta dot square. Okay, so that is it. I think from there the proof will come out right. M here cancel with m, a here cancel one time. These two can come here. I'll have 4g sine theta. So 4g sine theta equals to 3 a theta dot square. It's the same as 4g sine theta equals to 3a d theta dt all square. So that is the answer, and that is the proof. As simple as that, student. You see that, nothing to fear here. Then Roman 4, find the component of the reaction. Find the component of the reaction at the axis perpendicular to AO when theta takes the value pi on 4. Okay, student. Now, let us come up with a diagram so that you should see. We want the component of the reaction at the axis perpendicular to AO. So we are having something like this. We are having a diagram like this. So we are having the initial position of A here. Then when it is rotating like this, we have a final position of A here. Are you seeing? Then we can see that what? The weight is like this. It's having two components, one like this and one like this. So this is the weight. This is the weight. The weight there is how many? It's 2 mg. Is okay. Now let me come out with the component of the weight. Now the angle here is theta, right? The angle there is theta. Look at, if here is theta, it means that the angle that is horizontal here from here is theta. As you can see, this is the horizontal line. The angle that the horizontal line from with this line is theta. It will be the same here. It means that this component, since theta is adjacent, theta is already close to this one. It means that it's adjacent here. Therefore, the weight here will be 2mg simply what? Cos theta, and here will be 2mg sin theta. As simple as that. So cramming like that. Since the angle is close, is formed with the one of the component of that component should be cos because it's adjacent. It's okay. That side is adjacent, it's close to the angle. So that is it. So from there, I'm always having mg sin theta, mg, and mg cos theta. Those are the two components of the weight. Now, let us represent now the reaction first. This the component of the rate along is okay. This is the component of the rate tangent to the motion. So therefore, there should be what? Always. The reaction force always oppose the weight. It's always opposing the weight. So this one should be the reaction force tangent to the motion, and this one should be the reaction force normal to the motion, or the radial reaction force. Is okay. But they're asking for the reaction component because the reaction is having two components, one which is tangent and one which is radial. I'm just showing it. Reaction tangent opposes the tangential weight, radial opposing the radial weight. Then from there, we are asking to find the component of the reaction at the axis perpendicular to AO. Where is AO? This is A. This O. AO. Which component of the reaction is perpendicular to AO is which one? It cannot be the radial. The radial is along AO. So it is a tangential component of the reaction force, which is what? Perpendicular. This is it. Perpendicular to AO. So I'm using this one. Is okay. So by applying Newton's second law, I'll apply the second case. I'll have what? The summation of forces equals to MA. And that A should be what? A tangential, because I'm taking tangential components. So it means that what? I'll have 2 mg sin theta minus RT equals to A tangential. Is okay. This one is count positive because the body is moving like this, so the positive direction is like this down. Therefore, the negative should be the opposite up. Okay, then A tangential, I told you that A tangential is dV all over dt. Then since the radius here is constant, it is A, it will be simply A what? Theta dot dot. So I have 2 mg sin theta minus RT equals to MA theta dot dot. But I need to find theta dot dot. The only way for me to find theta dot dot is to come back here. They prove that we did. I am having theta dot here dt. Remember that theta dot dot is d square theta dt square. It means that if I come back to this equation and differentiate it a second time, I will come out with d square theta dt squared. Therefore, I have my theta dot dot. So let us proceed. So let us find theta dot dot by differentiating the proof. Okay, it means that if I come here, I will apply d theta. I will differentiate all the equation. I will have 4g sine theta equals to d theta of 3a theta dot square. Okay. Now let us differentiate. Now what you should note here is that I'm differentiating to respect to t, but I'm differentiating theta. It means that I should introduce. You should know that word. When I'm differentiating, I should introduce d theta. dt is the same as d theta times d theta d dt. It's the same thing. D theta cancel, come back to dt, to d dt. It's okay because I should differentiate with respect to t, but I'm not having t here, so I should introduce theta, chain rule, d theta times d theta dt, so that I can now differentiate with respect to theta. Then I put d theta dt, which is theta dot. So that is what I will apply here. So you should not be lost. So when I will differentiate, I will have when I differentiate sine theta, I have what? Negative cos. I have cos theta, pardon, not negative. So I will have 4g cos theta d theta, as I told you, because when I differentiate, I will come up with d theta equals to 3a. Then when I will differentiate this, I will have 2 theta dot dot d theta. I hope it's making sense now. I put this 2 here, then I differentiate. When I differentiate theta dot, I have theta dot dot. Then I should put d theta since I'm differentiating with respect to t. Then I can cancel out d theta cancel here, making sure that d theta is different from 0 because the body is moving. It means that the angular speed cannot be 0. So I can cancel here without panicking. It means that what? My theta dot dot is simply equals to, or a theta dot dot even. A theta dot dot is simply equals to 2 cancel 1 time, 2 cancel 2 times. Is simply equals to 1/3 g cos theta. Is it now? Yes, 2g. Oh, cancel here. No, there is a 2 here. It's 2 all over 3g cos theta. Exactly. When I will make a theta dot dot. Why am I making a theta dot dot the subject? Because here I'm having already a theta dot dot. I want to replace directly. So with that value now, let us go and replace. Let us go and replace it. I will have 2mg sine theta minus rt equals to m. How I'm putting a theta dot dot, I will put what? 2 all over 3g cos theta. I hope that is making sense. So, okay. Then now I'm looking for rt, right? I will make rt the subject. It means that rt will be equals to what? I bring this one here, I bring this one here. I'll have 2mg sine theta, bring this one here, minus 2mg cos theta all over what? All over 3. Then remember that theta should take the value pi all over what? Pi all over 4. Pi over 4 is 45 degrees. Okay. So let us replace. It means that our tangential component of the reaction force will be simply equals to sine pi over 4 is root 2 on 2. I will have 2mg root 2 all over 2 minus 2mg root 2 all over 3 times 2, which is how many? 3 times 2 is how many? 6. Okay. From there now, I can do the LCM. So 2 first of all cancel. I have mg root 2 minus 2mg root 2 all over 6. So 1 is the same as 6 all over 6. Is it now? 1 is the same as 6 all over 6. So it's the same as 6 mg root 2 all over 6 minus 2 mg root 2 all over 6. Same denominator, I can subtract the numerators. Okay. 6 minus 2 is how many? 6 minus 2 is 4. I'll have 4 here. Mg root 2 divided by 6 is okay. Then 2 can cancel. I'll have 2 mg root 2 divided by how many? 3. So that is the answer, Newton. That is the final answer. 2 mg root 2 divided by 3. As simple as that, student. So that is the final answer. Now let us proceed to the next question. The question for this year, we are having a uniform rod OA of mass m and length 6a can rotate freely in a fixed vertical plane about a fixed horizontal axis 2O. A uniform circular disc of mass 12m and radius a is clamped to the rod so that its center C lies on the rod and its plane coincides with the plane in which the rod can rotate. when OC equals to x. Roman 1. Find in terms of m, a, and x the moment of inertia of the system about the horizontal axis through O. Okay, I think this one is quite easy. I'm having a road OA. I'm having a road OA, and the mass of the road is m. Of length, we are having the length of the road to be 6a. The length of the road is 6a. Rotate freely in a fixed vertical plane about a fixed horizontal axis O. It means that the axis of rotation here is at O. Uniform circular disc of mass 12m and radius a is clamped to the road so that its center C lies on the road and the plane coincides with the plane in which the road can rotate. It means that the disc and the road are in the same plane and they coincide. So it means that the center of the disc may be somewhere here. This is the disc. Here is okay. Voilà. And where the radius, they gave the radius of the disc to be a and the mass of the disc to be 12m. Okay. Then they are saying that the distance from O to C is the center of the disc. The distance from O to C is how many? Is x. Then they are asked to find in terms of m, a, and x the moment of inertia of the system about the horizontal axis to O. Okay, student. Okay. Nothing to fear here. It means that I want to calculate the moment of inertia. I want to calculate the moment of inertia of the system about what? About one of the n, or about an axis passing to O. Here I'm having the system is made up of a disc and a road. So what am I supposed to do? I first of all calculate the moment of inertia of the road about the axis O plus the moment of inertia of the disc about the axis O. That is it, as simple as that. Then the moment of inertia of the road about the axis O is simple. O here is one of the end of the road. It's the same as calculating the moment of inertia about one of the end. We calculated it already. I think it was if I remember, it was IA equals to 4 all over 3 big M A square. Is okay. So we should now do only a correspondence here to come out with the moment of inertia of the road about O. Now the mass of the road, they gave the mass of the road to be where is it? M. It means that here I will simply replace 4 all over 3. Rather than putting big M, I will put small m. And they gave the length of the road is 6a. Remember, when we're calculating this one, you should cram it all. When we're calculating the moment of inertia of the road about the NA, the length was how many? The length was 2a. Now the length is how many? Now the length is 6a. So I will say 2a should be equivalent to how many? 6a. Therefore, that length, the new length now should be 3a. I come and put here 3a, then I put square. As simple as that. And then the answer will be what? I'll have a 9 here, 3. I'll have 4 all over 3. M 9a square. 3 can say 1 time, 3 can say 3 times. 4 times 3 is how many? 12 ma square. So that is the moment of inertia of the road about O. Then the moment of inertia of the disc about the NO will be what? The moment of inertia of the disc about the NO, I will do parallel axis theorem. Why am I saying that? Because first of all, calculate the moment of inertia of the disc about its center G is okay, plus the distance separating the two parallel axes is what? X. So plus the mass, which is 12m, the mass of the disc, times the distance separating the two parallel axes, which is how many? Which is x. This is it. Which is x what? Square. Now the moment of inertia of the disc about the center, remember it was how many? Half big M radius square. And then the mass is how many? Is 12. So I'll only replace 12m. And the radius of the disc is a square. Then plus 12 ma square. Okay. Then okay, let us substitute here. I'll have 6 ma square. Okay. Plus 6 ma square plus 12 ma. Pardon, here is x. Here is x square. Here will be x square. Okay, so that is it. Therefore, the moment of inertia of the system about the axis of rotation O will be simply equal to, I should add these two. It will be simply equal to 12 ma square plus 6 ma square plus 12 mx square. Is it making sense? Okay. Then 12 plus 6 is 18. I'll have 18m a square plus 12m x square. As simple as that. 18m a square plus 12m x square. What is common there? I think 2 is common. Yes. Even 6 is common. So 6m is common. I will stay with 3 here. Is it 3a square plus 2x square. So there is a moment of inertia of the system about one of its axes O. Then I want to show that the system of the so that the distance of the center of mass of the composite body is the system, the rod and disc system of the composite body from the point O is, okay, let us go and calculate the center of mass. Okay, let us calculate the center of mass very fast. I can let me put it here so that I should not forget. Okay, as we all know that what it's an horizontal distance, so the distance from the center of mass of the system to O is horizontal distance, therefore they are talking about what? X bar. And X bar, the first mass here is the mass of the disc, which is how many? 12m. Then the distance from the center of the disc, which is the center of the disc to this the axis of rotation, which is O, is simply x. Then plus the weight of the rod is how many? M. And the distance from the center of the rod is how many? 3a. Then divided by 12m plus how many? Plus m. So making the answer here to be 12mx plus 3m a divided by 13m. Okay, we can also hear that x bar m we cancel here. Now factorize it. I'll have 1/3 into 12x plus 3a. I think there is a proof now. 1/3 into 3a plus 12x. There is a proof. As easy as that, you have your 2 marks. Then Roman 3 for 5 marks. The period t of small oscillations of the system is given by, we are having t square equals to t square g a plus 4x should be equals to 8 pi square 3a square plus 2x. Exactly. So that is 5 marks. We are asked to find to show that the period of a small oscillation of the system is this. Now, to show this, we all know that what the period of oscillation, the general formula for the period of oscillation of any system is given at 2 pi square root of what? Moment of inertia about any axis, potential energy. So that is 2 pi square root of moment of inertia about any axis, potential energy is what? mgh. Okay, so that is it. Then do I know already. I will replace directly. Period will be 2 pi square root of, okay. Moment of inertia about which axis? The axis here is the axis that we calculated about O. So that moment of inertia about O was, if I remember this in now, so it was 6m into 3a square plus 2x square divided by the mass. The overall mass is the overall mass was how many? 13 now. Yeah, 13m. Then G. Then H. Remember, I told you that H is the distance from the center of mass to the axis of rotation. So X here is our X bar. It's simply our X. Here is simply our X bar. X bar, and the X bar was how many? It was 1 over 3. What is it? Yeah, 1 over 3. 3a plus 12x. So that is it. So let us see if the proof will come out. 13 first of all cancel here. M cancel here. Yes. Then 3, I can factor 3, I'll have 2 pi square root of 6 into 3a square plus 2x square divided by, I can factor 3 here, I will stay with a plus 4x. 3 cancel here 1 time, 3 cancel here 2 times. Okay. Then if I square both sides, I'll have t square equals to 4 pi square in bracket. In bracket 2 into 3a square plus 2x square divided by a plus 4x. Let me see the proof. Pardon, there's a G here like this, please. This G here, okay. Let me see the proof. If the proof is already coming out. Yeah, the proof is coming out. If I cross multiply, I will come out with the proof. I will have t square g into a plus 4x equals to, these two come and multiply, I will have 8 pi square. You see now? 8 pi square into 3a square square plus 2x square. Final answer. Exactly as in the proof. So now let us proceed with the last sample question I want us to do here. I even remember this question because it was my year, June 2021. So I will not lie to you that I answered this question. No, I did not answer it because I was having no idea about the question because in our time we're not even having a further math teacher. So when I was asking even to the math teacher, I was saying that A grade is not 100 over 100. So but you people have the chance to that there is school for all now that can solve this type of question for you people. Now, question 6: a uniform square laminar PQRS has sides of length 2a and it is of mass km, where k is a positive constant. The laminar is free to rotate in a vertical plane about a horizontal axis 2p. The laminar is slightly displaced from its position of unstable equilibrium, given that the component parallel and perpendicular to PR of the reaction at the axis when PR makes an angle of pi all over 4 with the upward vertical 2p are x and y respectively. Roman 1, find x and y in terms of k. Now, this question, we are having what? A laminar. A laminar, I think, is in form of a square. Is okay? So let me first of all try and represent the laminar here. Represent the laminar. P, Q, R, S. That is it. And here should be the center of the laminar. Let me call that center to be O. And the laminar is of side A. After drawing our laminar, now they are saying the next question is okay. So after drawing our laminar, they are asking us. They are saying that the laminar is slightly displaced from its position of unstable equilibrium, given that the component parallel and perpendicular to PR of the reaction at the axis when PR makes an angle of pi over 4 with the upward vertical 2p and x are respectively. Roman 1, find x and y in terms of k. Okay, I think that this position should be the stable position of the laminar. So I should put it on an unstable position. Unstable position means that what? I can take this stable position, I try to displace it like this, like we have something. I think this should be the unstable position they are talking of. Yeah, this is an unstable position. It's from this unstable position that I displace it slightly. It's okay. You see that this unstable position, this is P, R, where this should be the center. When I will displace it slightly, you see that PR will form what? A certain angle with the initial position of PR. That angle now is theta. You see that our resultant figure here will be something like that. Our horizontal figure will be something like that. Where is P? Here this should be Q and this should be S. Are you seeing? So that is it. So let me come here and draw a free body diagram. It means that the important points here should be P, R, then the vertical here up like this. Then remember that this is point what? O. This is the initial position of O prime, and this one is O, the final position, and then it's making an angle of theta. As I said, who is responsible for turning? Who is describing a circular motion when the laminar is turning? Look at, when the laminar is turning, like I'm having this, if this is the laminar, when I'm turning like this, let's say this is P now, this is R, this is the unstable position. When I start turning like this, look at the center of the laminar, which is responsible for the center of mass of laminar, which is responsible for the turning. We describe what a circle is, okay, and the center of mass is at this position, where the distance from P to R, from P to O, this distance from P to O, I can call it R. Why am I calling it R? Because it will be the center of the rotation described by what? The center of the rotation of the circle described by what? The center of the laminar. Like when you observe, when this thing is turning, when you observe the center of the laminar, you observe the path that the center of the laminar is describing, it will form what? A circle. Okay, so you see that what? At the center of the laminar, there will be path, there will be the weight. The weight will have two components, one acting along PR and one acting perpendicular to PR. Perpendicular to PR like this. One acting here, one acting perpendicular to PR. It means that this is the weight. The weight K, M, G. So that is it. So That is it. One acting perpendicular to PR, the way should be straight, and one acting along. So that is it. Now to find out the component of the weight, you see that what? This angle here from Z principle, from this one, Z principle, you see that theta here is theta here. Look at, it's the same thing here like this. I'm going like this, Z. It means that this is the theta again here. It means that this side here is what? Adjacent to theta. Therefore, it should be that component having cos. So I have kmg cos theta, and this one therefore should be kmg sine theta. Okay, so with that, now let us represent the component of the reaction force. It's okay, let us represent the component of the reaction force. As I told you, the component of the reaction force always acts opposing the weight. It means that there will be one here like this, there will be one component like this along PR, which is, I think that component, they named it was X or Y. Let me see, let me not slightly displace, given that the component parallel, okay, that one is X, therefore this one like this, opposing this one up like this, should be Y. Okay, so that is it, as simple as that. You come out with a diagram. Now from the diagram I will now apply Newton's second law. From Newton's second law, we all know that what? For a body undergoing a rotational motion, sum of forces acting on the body should be equal to MA, where A has two components, radial and tangential. So let us apply Newton's second law along the forces parallel to PR. So we'll take along this parallel to, okay. So when I will resolve the forces parallel to PR, okay, means that I will have, this is PR. So forces that are parallel to PR, I'm having X and kmg cos theta. Okay, then which one will count positive? To know the one that will become positive, look at this is how this is the circle like this. Have you seen? It means that what? PO is what? PO is the radius of the circle. It means that the radius is being increased outward like this. We increase the radius like this. The radius increase outward. It means that forces that are going upward like this should become positive. And you see that even for this one, the circle, the angle theta is increasing like this downward. The angle theta is increasing like this downward. It means that all forces going downward like this is also count positive, because angle increases like this. So those are my directions, positive direction from my diagram. It means that here, when I will apply Newton's second law along forces parallel, it means that X here will become positive, minus kmg will become negative, kmg cos theta equals to the mass, which is km. Then is which acceleration? Here you are talking about radial acceleration or normal acceleration. Yeah, because the acceleration is directed toward the center. Now you should know that what? The radial acceleration is always negative because it's directed toward the center. It is negative what? RO omega square, which is what? Negative R theta dot square. I will replace it here. I have X minus km g cos theta equals to negative km R theta dot square. Okay, student. So that is it. That is already my first equation to find X. When I will resolve the forces along PR, forces parallel to PR, I will come out with this equation. Now I need to find, I have two unknowns here. I need to find R and theta dot square. Now to find R, as I said, R is the radius. R is the radius of the circle described by the center of mass of the lamina. So how can I find R? It's easy. Look at, if the side here is 2A, it means that if I divide it like this, here will be A and here will be A, because the side is 2A, 2A, 2A. Is okay? And the radius is the distance from the center of rotation, which is P, to the center of mass, which is O. So this is the radius. From here to here is the radius. Okay, and I can still represent it on the lamina here. Look at, this is PO, radius. And that radius is equal to what? From Pythagoras theorem, the radius is simply equal to square root of A square plus A square, which is simply equal to A root 2. So that radius, I'll put it here, R is simply equal to A root 2. That is the first unknown already. Then I need also to find theta dot square. And to find theta dot square, the only way to find theta dot square is to apply what? The law of conservation of energy is there that theta dot square will come out. Yeah. So applying the law of conservation of energy, you see that what? The potential energy which is being lost will be equal to the kinetic energy gained by the laminar. Exactly. Now, another potential energy is what? mgh will be equal to half. Remember, kinetic energy was what? Moment of inertia about the point of pivot, which is p, times omega square, which is theta dot square. Now, am I having IP? No. So I have another two unknowns here. I'll first of all come and calculate h. H is there. H is what? The loss in height. Is okay. Now let us come back on our diagram and see how the height, how the height is being lost. Look at the initial position of the weight. The initial position of the center of mass, this is it. If you remember the initial position of the center of mass, this is it. When it was up like this is it. When PO was up and straight, this is the initial position of the center of mass, and this is the final position. I named the initial position of O to be O prime and the final to be O. Then you see that there is a loss in height from this position. Let's take this as our reference. Let's take this as our reference line like this. It means that what? If this is a reference line, it means that initially the center of mass of the lamina was at a height, this is it. And finally, this is alright, and finally, it's at this height now. And finally, this is O prime, and then this is O. And finally, it is at this height. So the loss in height there will be what? From year to year minus year to year. So this is the loss in height here, which is H. I hope you understand it. Means that initial position O prime of the center of mass of the lamina, final position, this is O, this is it. It means that it left from year, it left from year to year. It means that the loss in the height should be this distance. I will take from year to year minus year to year to have H. So my H is simply equals to what? My H is simply equals to P O prime minus P O prime minus this distance P. I will call this one I will call this point here maybe M. Okay, minus P M. Is okay? So that is it. Okay, then we all know that what? PO prime. The distance PO prime, look at, is this a circle, right? It describes a circle. The distance from the center to the circumference of the circle is where? The radius. Look at this, a circle. Is okay. That part, one of the parts of the circle, this is it. So the distance from the center of the circle to the radius is R. Then the distance PM, this is PM. PM. You see that PM here is the adjacent of this angle. It's forming a small right angle triangle here like this, where PM is the adjacent of this. Therefore, adjacent means we should use cos. And the hypotenuse of that angle is R. So it will be R cos theta. Therefore, I will have R into 1 minus cos theta. Remember that R is what? R is A whole 2 into 1 minus cos theta. That is the value of H. I come and put it here. A root 2 into 1 minus cos theta. As simple as that, I have the value of R. So nothing difficult there. Now with the value of R, with the value of H, pardon. With the value of H now, I should go and look for the value of IP. IP, the moment of initial of the lamina, of the square lamina from an axis passing to point P. Now, I tell you that what, when you want to calculate the moment of initial about a figure, the moment of initial about of a figure about one of its ends, you first of all calculate, you use parallel theorem, you first of all calculate the moment of initial about the center. About the center is okay. You calculate first of all the moment of initial about the center of that figure, plus you take down the mass of the figure. The mass of the lamina, if I remember, the mass of the lamina is Km. Then the distance separating the two parallel axes. These are the two parallel axes. The axis passing to P and the axis passing to O. That distance is what? R. Then I square it. As simple as that. Then we should now come out with the moment of initial about the center of the lamina. Now, normally they were supposed to give it in the question. It means that there was a small mistake. They were supposed to give the moment of initial about the center of the lamina of a square. Moment of initial about a square from the center. So I think it is 1 over 12 m a square plus b square. So that is it. It's not inside the formula below they were supposed to give it. Now here our site at 2a. It means I will have 1 over 12 m here is what? Is km into 2a all square plus 2a all square. So I will have 1 over 12 km 2a square plus 2a square will be 4, 4, 8. It will be 8a square. So that is it. So 4 can cancel. When 4 will cancel, I will have 4 cancel. I will have 2 all over 3 km a square. So that is the moment of inertia of the square about its center. When I have now the moment of inertia of the square about its center, I can now come and calculate the moment of inertia. Yes, I can now come and calculate the moment of inertia of the square about the point of pivot P. So I will have here simply 2 all over 3 km a square plus km. Remember that r is what? R is a root 2. When I will square it, will be 2a square. So okay, then I will do the LCM here. I will have 3 times 2, 6, 6 plus I will have 8 all over 3 km a square. So that is the moment of inertia of the lamina about what? About its pivot P. Okay, then when I have this now, I come and substitute in which equation? I should come and substitute here and find the value of theta dot square so that I can come and replace it here. Then I find the value of x. As easy as that. So let me come here and put my value. It means that I will have m. I will have m g. Rather than writing h, I will write a root 2 into 1 minus cos theta equals to half into 8 all over 3 km a square. Yes, then theta dot square. Now remember that the angle theta, the value of theta is what? Pi over 2. So theta is pi all over 4, pardon, and pi over 4 is 45. So cos 45 degree will give us what? Root 2 all over 2. So I'll have mg a root 2 1 minus root 2 all over 2 is equals to 2. We cancel that. I'll have 4 all over 3 km a square theta dot square. I want to make theta dot square the subject. Okay, I will first of all try to simplify here. This root 2 will enter here. I'll have a can cancel 1 time. Yeah, okay. Remember that, please, the mass here is km. Okay, remember that the mass is km. Okay, it means that even m here will cancel here, k cancel here. Okay, so I will stay with theta dot square will be equal to 3. Is it? Yeah, it will be equal to 3 root 2 all over 4 a into 1 minus root 2 all over 2. So that is theta dot square. I hope you're understanding. So I'll make theta dot square the subject will be 3 root 2, there's g here, 3 root 2 g all over 4a. Voila. So that is it. So if I want to put this root 2 inside, it will be 3 all over 4a g into root 2. Root 2 times root 2 is minus 1. So root 2 times root 2 is 2. 2 divided by 2, 1. So that is it. Now with that value now, we should now come and replace with the value of theta dot square. I will come and replace it. It means that my x is simply equals to kmg cos theta. I'll put it there. Minus km. R is what? R is a root 2 into theta dot square, which is what? Theta dot square is 3 g all over 1. I will stay with root 2 all over 2 minus k. Okay, a here cancel here. I will stay here, kmg goes. Okay, that's it. As simple as that, we'll come out with that. Then after that, I will have kmg. This is, we are simplifying. I will open the bracket here. I will have root 2 all over 2 minus root 2 times root 2 2. I will have 3 all over 2 here. Yeah, because 2 we cancel the 1 time. Then plus 3 all over 4 root 2. Okay, as simple as that. Then the allied terms here, I will have kmg into, look at these two allied terms, I can add them. LCM there is 4. 4 divided by 2 is 2. 2. Okay, I will have the value of x directly. So my x is simply equals to 4 is common there. I can factorize 4. I'll have kmg all over 4 into, when I factorize 4, you see that I will stay with 5 what? I will stay with 5 root 2, then minus how many? Minus 6. When I factorize 1 over 4 outside. So there is the value of K. You put your new Newton because it's a force. So there is the value of X, pardon. There is the value of X. There, the component of what? The component of the reaction force, which is what? Parallel to PR. Okay. Now, without wasting time, let us now go and find the value of Y. To find the value of Y now, I will apply Newton's second law now what? Along perpendicular components. So, let us apply along perpendicular forces to PR. Now along perpendicular forces, you see that what? Summation of F will be simply equals to what? Perpendicular. Which forces are perpendicular here? We have KMG. Now KMG will become positive. Look at my positive references here. So KMG will become positive. And so I'll have KMG sine theta, then minus Y. You see Y is going upwards negative. Should give me KM what? Should give us KM. Then which acceleration? Tangential. Is it tangential acceleration or radial acceleration? How am I going here? Yeah, tangential acceleration. It's tangential acceleration because look at tangent to the motion. This is the circle. This is how the motion is going. It's tangent. Tangential acceleration. And we all know that what tangential acceleration. Tangential acceleration is the same as what? R theta dot. I will come and replace my R theta dot. And I already know the value of R. So the value of R is A root 2 theta dot. Now the only unknown here now is to find theta dot. As to find theta dot. And the only way to find theta dot is to apply what? Newton's second law. Newton's second law, but you apply case 2. Is it okay? Exactly. You should apply case 2 of Newton's second law. So from case 2 of Newton's second law, you see that what? Case 2 says the summation of moment of external forces acting on the lamina will be equal to what? The moment of inertia about the pivot P, theta dot. Are you seeing where theta dot is coming from? It's from there that we can calculate it. The first thing to calculate here is to come out which force is having a moment here. So you see that the force having a moment here is the force which is perpendicular to what? To PR. Is okay because it's having a perpendicular distance from P. And that perpendicular distance from P is what? Is the radius of the circle described by the center of mass of the lamina. And it is what? R. So I will have directly KMG sine theta times what? R should be equal to IP theta dot. And that, remember that sine theta is what? Is simply root 2 all over 2. And A is what? R is what? R is simply A. It means I can already make my theta dot. I'll have theta dot times moment of inertia about P, which was 8 all over 3 km A square equals to KMG root 2 times root 2 is 2 divided by 2. It cancel. So I'll have here A. So KM cancel with KM here. A here cancel one time. It means my theta dot is simply equals to 1 minute 3G all over what? 3G all over 8A. So that is the value of theta dot. 3G all over 8A. So I'll carry now this, I'll come and replace, I'll carry this, I'll come and replace here. I'll have, let me wipe this. I will make Y the subject. Y is simply equals to, I bring this one, I'll have KM. Do you remember that sine theta is what? Root 2 all over 2. I bring to our minus KM A root 2 in bracket theta dot, which is what? 3G all over 8A. Okay. Now, you see that KMG root 2 is common. I will stay here with half minus 3 all over 8. Remember that A cancel here. Okay. The LCM here is 8. 8 divided by 2, 4. 4 minus 3, 1. So making the answer to be KMG root 2 divided by 8. Okay. Then I come and put it here. I put directly my X and my Y here, pardon, to be KMG root 2 divided by A Newton. So that is the perpendicular component of the reaction force about the line PR. Okay, that is all. Let us now do our last part of our. Given that X is 5 root 2 minus 6 and Y is root 2, by the end there is bracket here mg, and Y is root 2 all over 2 mg. Is okay. We are asked to find the value of K. So there is Roman 2. So given that x equals to this and y equals to this, find the value of k. So comparing the x they gave with my own here, you see that what I can use, it means that I can equate this. So comparing implies kmg all over 4 into 5 root 2 minus 6 should be equal to what? 5 root 2 minus 6 in bracket mg. I will do same here down. It means that kmg root 2 all over 8 should give us root 2 all over 2m mg. So this is what they are saying. From here now, by doing what the equivalence here, you can now find the value of k. I can use this equation 1, equation 2. I can use any equation. I think the simpler one, there should be voila, it should be equation 2. K, pardon, mg here cancel with mg here, root 2 cancel with root 2 here. It means that k is simply equals to what? 8 all over 2, which is what? 4. So that is it. You can still verify this 4 with equation 1. I think with equation 1 you give us the same thing. mg here cancel with mg here. All this one cancel here. So I'll have k all over 4 equals to 1. K equals to 4. Now from there you are sure that the value of k is correct because it is respecting the two equations. So students, so that is all about moment of inertia. I really hope that it will really help you in the exam. So I think I did it's how many years? I did from June 2025 to June 2021. So that is already enough for you to understand moment of inertia. So we are together, School for All, and Mr. Tube wishes you all the best for your exam on Saturday.